I was actually thinking about the concept of a library the other day. Welcome to today's deep dive, by the way. I'm your host.
Hey everyone, and I'm your resident materials expert. Thanks for having me back.
Always great to have you. So, yeah, I was thinking about libraries, but not just your local branch. Imagine a library that contains every possible material in the universe. A literal library of matter.
Oh, wow. That's a massive library.
Right, massive. And if you walk into the organic wing, the section for the stuff life is made of, the carbon chains, medicines, plastic.
Yeah, the organic chemistry section.
Exactly. That wing is absolutely overflowing. Like, we have computationally generated billions of these things. It's this chaotic mess of abundance. It really feels like we've read almost every book in there.
That makes total sense. I mean, organic chemistry is essentially Lego. It has very flexible rules. You can just snap carbon pieces together almost infinitely.
Exactly. Lego is the perfect word for it. But then you walk over to the other wing.
The inorganic wing.
Yes, the wing for functional inorganic materials. This is the hard stuff. The ceramics, the metals, the exact stuff we need to build quantum technology, superconductors, next-generation batteries. And you walk in there and it's
quiet.
it's crickets. It is surprisingly empty.
It is a stark contrast, for sure. And, it's not because the elements aren't there. We have the whole periodic table to play with.
Wow.
It's because the structural complexity of inorganic materials is just a complete nightmare to navigate.
And that, right there, is the friction point we're digging into today. Because for the longest time, finding a new material that does something cool, like conducting electricity without resistance.
Room temperature superconductors, the holy grail.
Right. Finding that was basically like winning the lottery. You just mixed stuff up, heated it to 1,000 degrees, and hoped you didn't just make really expensive dust.
Trial and error. I mean, it works
Yeah.
eventually. That is how we got bronze and steel, but it is incredibly slow. And in the race for quantum computing, we just don't have time for slow anymore.
No, we really don't. So today, for you listening, we are talking about a massive shift. We're moving from discovering materials by pure luck to forcing them into existence with artificial intelligence and atomic precision.
And we are looking at two sources today that, frankly, feel like science fiction.
They really do. The first is a groundbreaking paper from Nature Materials. It was published just last month, February 2026.
Super recent.
Yeah, hot off the presses. This is a massive collaboration involving researchers from MIT, Oak Ridge National Laboratory, and a few others. And they are introducing a new AI model called SCIGEN.
That section, right. Which is essentially hallucinating new, stable, inorganic materials into existence.
And to pair with that, our second source is a report from ACS Materials Letters from October 2025. This features work by physicists and chemists at Auburn University on a totally new class of materials called electrodes.
So if you think about it, on one hand, we have the architect, which is SCIGEN, designing the cage.
Okay.
And on the other hand, we have the Auburn team taming the beast inside the cage, which is the free electron.
I love that analogy. If this all works, the periodic table stops being a list of ingredients and starts looking a lot more like a suggestion box.
That's a great way to put it, a suggestion box.
Let's start with the architect then. SCIGEN. This comes from the MIT and Oak Ridge team. What exactly is the core problem they were trying to solve here? Like, why can't I just sit down at my computer and type, "Hey, ChatGPT, build me a room temperature superconductor"?
Well, the problem is geometry. In organic chemistry, like I said earlier, you snap pieces together. But in inorganic crystals, the properties, whether a material is magnetic, conductive, or insulating, are dictated entirely by the precise geometric arrangement of the atoms in 3D space.
So it's not just the recipe.
Exactly. It's not just what is in the mix, but exactly where it sits.
Shape is destiny.
Precisely.
Yeah.
Shape is destiny. And designing stable materials that hold a specific, complex shape is incredibly hard. That is where SCIGEN comes in.
SCIGEN. Break down the acronym for me.
It stands for Structural Constraint Integration in a Generative Model.
Okay, bit of a mouthful. But generative model implies it's similar to the AI art tools that everyone is using right now. Mid-Journey, things like that.
It is very similar, actually. It uses what's called the diffusion model.
Okay, for the listener who maybe hasn't gone down the deep AI rabbit hole recently, unpack diffusion in this context.
Sure. Imagine you start with a picture of static. Just random snowy noise on an old television set.
I'm picturing it.
The AI has been trained on millions of images to see patterns in that noise. It slowly removes the static step by step over many iterations until a clear image emerges out of nowhere.
Right, it do noise.
Exactly. SCIGEN does exactly that same process, but instead of pixels, it's working with atoms. It starts with random atomic noise in a 3D space and denoises it into a stable crystal structure.
But here's the twist, right? Because if I just tell an AI to make a crystal, it would make something really boring. Like it might just reinvent table salt.
Yeah, we don't need an AI for table salt.
Right. These guys didn't want boring. They wanted magic.
They wanted specific quantum playgrounds. And this is where the constraint integration part of SCIGEN comes in. They use a masking strategy.
Walk me through that. Masking.
Think of it like a Sudoku puzzle.
Okay, I play a lot of Sudoku. I'm with you.
In Sudoku, you start with some numbers that are fixed in pen. You cannot move them. Those are your constraints. Your job is to fill in the empty squares around them in pencil so that the whole grid makes sense mathematically.
Right, and if you move the fixed numbers, you break the whole puzzle.
SCIGEN does this exact thing with atoms. The researchers essentially tell the AI, we need a specific lattice shape, say a honeycomb pattern. Those specific atoms must be there. That's your fixed grid in pen.
Got it.
Then they let the AI hallucinate the rest of the atoms in the empty spaces to stabilize that exact structure.
So the AI is free to be creative with the filler atoms, but it's forced to adhere to that master geometry.
Exactly. During the generation process, every time the AI tries to clean up the noise, the system masks the constrained part. It forces those critical lattice atoms to stay exactly where they're supposed to be.
Oh, I see.
And then the unconstrained atoms naturally find the most stable, energetic positions around that scaffolding.
You're essentially bullying the physics into the shape you want.
In a way, yes, you're constraining it. And they focused on some very specific shapes called Archimedean lattices.
Archimedean lattices. It sounds ancient, like something Indiana Jones would be looking for in a temple. Why these specific shapes?
Because these shapes are where quantum physics gets really weird. The researchers specifically looked at triangular, honeycomb, and something called kagome lattices.
Kagome. Am I saying that right?
You are. It's named after a traditional Japanese basket weaving pattern. It's this intricate pattern of interlaced triangles and hexagons.
Okay, beautiful basket. But why does a basket weaving pattern matter for high-tech quantum computing?
Because, remember, geometry dictates electron traffic.
Mhm.
In a standard square grid, electrons move pretty smoothly. But in a kagome lattice, the geometry creates a massive traffic jam. The electrons get what physicists call frustrated.
Frustrated. That's an actual technical term.
It actually is magnetic frustration. Imagine you have 3 magnetic atoms at the corners of a triangle.
Okay.
Atoms generally want to align their magnetic spins opposite to their neighbors. Think of it as wanting to face away from the person standing next to you.
Okay, they're antisocial atoms.
Right. So atom A points up, atom B points down. But atom C, the third one in the triangle, has a big problem.
Because it's a triangle.
Exactly. If it points up, it conflicts with A. If it points down, it conflicts with B. It's stuck. It literally doesn't know what to do. It is frustrated.
And I assume that subatomic confusion is somehow useful for us.
Incredibly useful. When electrons can't settle into a standard boring order, they enter these exotic quantum states. They can form things called quantum spin liquids, or they create what we call flat bands.
Flat bands. That sounds like an obscure 90s indie rock station.
It really does. But in physics, a flat band means the electrons have a massive effective mass. Their kinetic energy gets quenched.
Meaning they stop moving.
They stop zooming around, yes. And because they aren't zooming past each other, they start interacting really strongly with one another. That strong interaction is the primary seed for things like high-temperature superconductivity.
Wow. So SCIGEN isn't just making random rocks. It's specifically hunting for these frustrated geometrical layouts where things like superconductivity might be hiding.
Exactly. They also looked at Lieb lattices, which are a variation of the square lattice that are notoriously difficult to find in nature. SCIGEN used this adaptive strategy to slowly relax the rules and let the chemistry find a way to make them stable.
Let's talk about the scale of this operation then, because usually a materials lab might find, 1 or 2 candidate materials in a year? What did SCIGEN actually produce?
The number is staggering. It computationally generated 10.06 million materials with Archimedean lattices.
10 million. That's not a library wing anymore. That's the Library of Congress.
It is. But having the digital data isn't the same as having the physical material. You obviously can't synthesize 10 million things in a lab. You need a funnel.
Survival of the fittest. How did they whittle 10 million down to something usable?
It was a pretty brutal audition process. First was pre-screening, just basic chemical rules. Is the charge neutral? Do the atoms actually fit in the physical space without overlapping?
Sort of a basic, do you obey the laws of physics test.
Right. And that alone cut the 10 million down to about 1.01 million instantly.
So 90% failed the basic reality check.
Exactly. Then they took a subset of that, about 26,000 candidates, and ran them through high-throughput density functional theory calculations, DFT.
And for those of us not in a materials lab, DFT is basically a virtual stress test.
That's a great way to put it. It's a heavy-duty quantum mechanical simulation to see if the structure would actually hold together under real-world energetic forces. And here is the really impressive part. 53% of those generated structures were found to be stable.
53%. That seems, I don't know, is that low?
For a generative model proposing complex materials that have literally never existed before, that is a massive hit rate. Usually finding a new stable material is like finding a needle in a haystack.
Okay.
This is like the AI handing you a handful of hay, and half of it turns out to be needles.
Okay, that definitely puts it in perspective. That's wild.
And they went even further. They used a graph neural network, a GNN classifier, to check for magnetism. They found that 41% of those relaxed, stable structures were likely magnetic.
So we have this machine that churns out millions of candidates, filters them through physics engines, and hands us a clean list of stable, magnetic, quantum-ready materials.
Yes.
But, and this is the big question for me, did they actually make any of them? Because I can simulate a dragon on my laptop, it doesn't mean I can keep one as a pet in the backyard.
They absolutely did. They synthesized 2 completely more materials in the lab just to prove the pipeline works.
Drumroll, please. What are they?
Material number 1 is a titanium-palladium-bismuth compound. The specific formula is TIP-P 0.22 by 0.88.
Catchy. Rolls right off the tongue.
I know, not the best marketing name. But this one was synthesized and found to be paramagnetic, meaning it's weakly attracted to magnetic fields.
And the second one?
Material number 2 was a titanium-palladium-antimony compound, Ti 0.5 PD1.5 SB. That one was found to be diamagnetic, which means it is repelled by magnetic fields.
Now, let's be real for a second. Were they perfect? Like, did the computer simulation match the physical reality 100%?
Not 100%, no. The source paper clearly notes that the experimental results had slight deviations from the perfect model. Real life is messy. There was some atomic disorder, some competing phases where the crystal didn't form flawlessly.
Sure, the AI predicts this perfect platonic solid, but the chemistry lab gives you something slightly gritty.
Exactly. But the key takeaway here is that SCIGEN proposed chemically plausible motifs. It wasn't just hallucinating impossible objects. It gave a valid, working blueprint that human chemists could actually take into the lab and build. It creates a starting point where none existed before.
So that's the structure, the lattice, the cage, as you called it. Let's shift gears now to what's happening inside that cage. This brings us to the second source, the research out of Auburn University.
Yes. This is where it gets really sci-fi. We're talking about electrides.
Electrides. I know it's not a sports drink, but it definitely sounds like one.
It does. But to understand an electrode, you kind of have to rethink how an atom works. Usually, as you know, electrons are tightly bound to a nucleus. They orbit it like planets around a sun.
Right, basic chemistry.
But in an electrode, some of those electrons completely break free. They move into the empty interstitial spaces of the crystal lattice, and they act as if they are negatively charged ions, anions, but without a nucleus attached to them.
Wait, so they're like ghost atoms?
Yes, ghost atoms is a brilliant way to describe it. It's just pure negative charge hanging out in the void of the crystal, acting like an independent atom.
But that sounds incredibly unstable. Electrons hate each other, they repel. If you don't have a heavy positive nucleus to anchor them down, should they just fly apart instantly?
It is incredibly unstable. That's always been the huge problem in this field. These are technically called solvated electron precursors.
Solvated electron precursors.
Right, and they are usually very fragile. If you look at them wrong, they degrade. They react with oxygen in the air, with moisture, with pretty much everything.
So what did the Auburn team figure out? How do you keep these ghosts from just disappearing?
They anchored them. They developed what they call Surface Immobilized Electrides. Instead of trying to make a freestanding 3D chunk of this highly volatile material, they attach these electron precursors to very stable 2D surfaces.
What kind of surfaces?
Specifically, they use diamond and silicon carbide.
Diamond.
Yeah.
The hardest, most stable stuff around. So they took the most flighty, ephemeral thing in physics, a free-floating electron, and they bolted it to the most durable thing in geology.
Precisely. It's this brilliant juxtaposition. And by doing that, they gained unprecedented control. The source paper describes two distinct configurations they can create on these surfaces, and this is the really big takeaway for this research. They can create islands or they can create seas.
Islands and seas. That's very poetic for a physics paper. Let's break that down. Start with the islands.
In the island configuration, the free electrons are clustered in isolated spots on the diamond surface. They are trapped there, highly localized. They cannot move to communicate with their neighbors.
And why is a trapped, lonely electron useful to us?
Because a trapped, isolated electron is a perfect candidate for a qubit.
Ah, the basic unit of quantum computing.
Exactly. Right now, keeping a qubit stable is a nightmare. It requires near absolute zero temperatures, massive cooling equipment, perfect isolation. But if you have these free electrons inherently stabilized by a diamond surface at much higher temperatures...
Because diamond handles heat really well. It's chemically inert.
Exactly. It suggests a clear pathway to much more robust, commercially viable quantum processors. You are essentially telling the electron, sit here, hold this quantum information, do not move. It effectively becomes a memory storage unit at the atomic scale.
Okay, so that's the islands. Computing power and quantum storage. What about the seas?
In the C configuration, they arrange the surface molecules so that the electrons spread out into wide, metallic sheets. They become completely delocalized. They flow freely across the surface like water.
And what is the practical application there? I assume it's not data storage anymore if they're moving around.
No, this is for chemistry, specifically catalysis. When you have a literal sea of free electrons available on a surface, they are extremely eager to react with things. They can drive complex chemical reactions, helping to break stubborn molecular bonds or form new ones much, much faster than traditional methods.
So we're talking about next generation manufacturing?
Smarter, faster manufacturing. The source specifically mentions using these porous electride structures to accelerate vital reactions for creating fuels, new medicines, or complex industrial materials. It's what they call tunable electron delocalization.
Tunable. That's the absolute key word there.
It is. You are literally telling the matter what to do. You adjust the spacing, you adjust the surface chemistry, and you tell the electrons, be a computer qubit or be a chemical catalyst. You say sit still or flow freely.
That is wild to me. We are micromanaging subatomic particles on a massive scale. It's not just observing physics anymore, it's directing traffic.
It really creates this incredible bridge between digital design and physical reality.
So if we zoom out for a minute and look at both of these breakthroughs together, you have SCIGEN from MIT and the Electrons from Auburn. What is the bigger picture here? How did these two completely separate papers talk to each other?
I think we are looking at the ultimate convergence of structure and function at the atomic limit.
Synthesize that for me. What does that mean practically?
Think about it like building a house. SCIGEN gives us the perfect scaffolding. It allows us to use AI to computationally design the perfect lattice, say that tricky kagome lattice we talked about earlier that forces atoms into these specific symmetry-breaking arrangements.
Right, that's the hardware. The frame of the house.
Exactly. And the Auburn research. That gives us the resident, the active agent inside the house. It gives us the ability to manipulate the free electrons on or inside those incredibly stable structures.
So you could theoretically use an AI like SCIGEN to design a completely novel lattice that is perfectly optimized to hold these Auburn electrons.
That is exactly the logical next step. Yeah. Imagine an AI designing a porous Archimedean lattice specifically shaped to host islands of free electrons for a next-gen quantum processor.
Yeah.
Or a honeycomb lattice custom designed to maximize the C effect for a very specific chemical reaction to synthesize a new cancer drug.
It's like we've been playing with those wooden alphabet blocks for centuries, and suddenly someone handed us a 3D printer and a subatomic soldering iron.
It completely changes the scope of human discovery. The SCIGEN paper explicitly mentions that during their generation phase, they found exotic magnetic orderings that human scientists had just completely missed.
Why did we miss them?
Because the search space was simply too big for us.
Right. We couldn't look through a billion haystacks by hand.
No human team could. But a diffusion model can. It doesn't search the haystack. It learns what a needle looks like from the training data and then just generates a new needle. And then, combined with the Auburn tech, we are learning how to thread that exact needle with pure electron energy.
It brings me back to that thought I had at the very beginning about the periodic table.
Go on.
Well, We usually think of materials as being rigidly defined by their elements. You're taught in school, this is gold, it conducts, this is rubber, it insulates.
Right.
But here, we're taking titanium and palladium, which are just standard metals, and making them paramagnetic or diamagnetic just by tweaking the microscopic geometry. We are taking electrons and completely detaching them from elements to act as independent tools.
You're absolutely right. We are approaching a point where the element itself is just a raw material. It's just a suggestion. The real property comes entirely from the design.
It's the difference between cooking and architecture. In cooking, the flavor comes primarily from the ingredients you put in the pot. In architecture, the strength of the building comes from the shape of the beams.
That's spot on. And we are just now getting the blueprints for the atomic architecture. The Auburn researchers use that word tunable.
Yeah.
We aren't just finding what nature gave us in the ground anymore. We are tuning matter like an instrument.
And with 10 million potential lattice candidates generated by a SCIGEN, we have a hell of a lot of tuning to do.
We really do. And remember, they only synthesized 2 of those 10 million so far.
Just 2.
Just 2 to prove it works. There are millions of potential superconductors, quantum magnets, and highly efficient catalysts sitting on a hard drive right now, just waiting to be cooked up in a lab.
That is both incredibly exciting and a little overwhelming.
That's the nature of the deep dive, isn't it? The deeper you go into the source material, the more you realize just how much is left to explore.
Absolutely. So let's wrap this up and summarize what we've actually found today for the listener.
Well, we've seen that generative AI, specifically diffusion models like SCIGEN, has basically cracked the geometry problem of inorganic materials.
Yeah.
It can force atoms into complex Archimedean lattices to create stable, functional quantum materials that humans might never have stumbled upon organically.
And we've also learned that we can tame the electron itself. The Auburn team showed us that by immobilizing solvated electron precursors on super tough surfaces like diamond, we can toggle between quantum computing bits, those islands, and chemical manufacturing catalysts, the Cs.
It really is a completely new state of matter for technology.
Which brings us to our final thought for you to chew on today.
Here's what I'm currently thinking about. For centuries, chemistry was fundamentally about discovery. We walked around the world, picked up a weird rock, and asked, what does this do?
Right, the discovery era.
But if AI can now hallucinate perfectly stable crystal structures that nature never even bothered to build, and if we can detach electrons to function as independent tools, are we transitioning to an era where we decide what properties a material should have first, and then simply print the atomic geometry to make it true?
Are we just discovering nature, or are we finally starting to edit it?
That is the big question.
Definitely something to think about the next time you pick up your smartphone. What shape are the atoms inside that screen, and who or what decided where they go? Thanks for joining us on the Deep Dive today.
See you next time.